Thank you, everyone, for joining our first EXOWORLD webinar. Today, we'll have a speaker, Jan-Vincent Harre, who's a PhD student at DLR, and he will talk to us about measuring orbital obliquity of warm Jupiters and Brown Dwarfs. The webinar will be recorded and will be uploaded to our project YouTube later on, so people who missed it can watch it again. And Jan, whenever you're ready.
Okay, great. Thank you for the nice introduction. So yeah, my name is Jan-Vincent Harre, if you don't know me. And yeah, as Christine said, this project was about measuring the orbital obliquities of warm Jupiters and brown dwarfs. Okay, so let's start with a very small overview. As the title suggested, we want to measure these orbital obliquities, which are the angles between the stellar spin axis, which is indicated here on the bottom right with the yellow arrow, and the planetary orbital axis, which is indicated with the blue arrow, and yeah, in these kind of systems. And for this purpose, I visited the Astrobiology Center at the NAOJ Mitaka campus in Tokyo, where I was supervised by Dr. Todoroki Hidano, who taught me everything I needed to know. So that was great. And I stayed there for the whole of April earlier this year. Okay, now let's get into some basics that we need to know. So first of all, the transit method. That is a very powerful method to detect planets. And actually, most of the already known exoplanets have been discovered using this method, namely around 3/4 of them. And so for the transit method, there's a small chance that a planetary orbit is aligned in such a way that it transits across its host star's disk, as seen from our point of view, and that I've indicated here in the bottom right. So we have a star and a planet with the orbit indicated with this white ring. And if the planet is correctly aligned, or the planetary orbit is correctly aligned with our line of sight, then we can see it moving across the stellar disk. However, we can't resolve this, but we can measure the brightness of the star, and that's what we do. So what we see here in the bottom right is a light curve, as it's called. On the y-axis, we can see the normalized flux. On the x-axis, we can see the orbital phase. And so we have it normalized to 1, basically. And when the planet starts to move in front of the stellar disk, then we will get this nice dip in the light curve, meaning that the brightness is decreasing because part of the stellar disk is blocked by the planet. And we can also calculate the so-called probability, or the probability that or the geometric transporability, as it's called, which we can estimate by dividing the stellar radius by the semi-major axis of the planetary orbit. So the distance of the planet to the star. And yeah, for Earth-like planets, this probability is around 0.5%, and for Jupiters, it is around 10%. And even though these probabilities are rather small, especially for planets that are further out from the star, the good thing is that we can observe with this method many stars at once, so, which is why we have so many planet detections from this method. The next one is the radial velocity method. And this method provided the second most exoplanet discoveries, with around 1/5 of the known exoplanets discovered using this method. And this relies basically on the wobble of a star in the sky due to, or which is induced by a planet. And the planet is not only orbiting the star, actually the star and the planet are orbiting their common center of mass, which means that also the star is moving on the sky away and towards us. And yeah, we can make use of this from with the Doppler effect and basically measure the velocity at which the star is moving away and towards to us. And this is indicated here in the figure on the right. So when the planet is moving away from us, then the star will be moving towards us, which will lead to a blue shift of the emitted light from the star. And then the opposite happens when the planet is moving towards us. The star will be moving away from us, leading to a red shift in the light coming from the star. But with this method, we can only observe one star at a time. So the magnitude of the shift of the spectral lines, or the redshift or the blue shift, from the usual wavelength in the spectrum can give us information about the velocity of the star towards or away from us, as I already mentioned. And this is indicated in the bottom right with a spectral line basically moving about as the planet and star are moving in their orbits. So the planet will now start to move away from us, meaning that the star moves towards us, leading to a blue shift in the spectral line. And then the opposite effect will happen when the star is moving, or when the planet is moving towards us and the star is moving away from us. And if we take measurements over the whole orbit of the planet, this can give us, for example, the minimum mass of the planet. And indicated here in the bottom left figure, we can see a radial velocity curve with the radial velocity in meters per second on the y-axis and the orbital phase actually in days on the x-axis. So we can see from this plot that there is an orbital period of around 3 days for this planet. And yeah, we have this usual sinusoidal curve which arises from the stellar motion. And yeah, here we can see the residuals from basically the differences between the data points and the model which we fit into it. So now there's also an effect called the Rossiter-McLaughlin effect, and that is basically a combination of radial velocity and transits. So if we observe radial velocity, or if we take radial velocity measurements during transit of a planet, then we will get the special effect, which is caused by the stellar rotation, basically, because one side of the star will be moving away from us and one side will be moving towards us. So basically this basically says that one side of the star is redshifted, or the light coming from one side of the star is redshifted, and the light coming from the other side is blue shifted, which is indicated here. And usually we can't resolve this. We can't resolve the stellar surfaces. But if there is a planet transiting, basically, then a small portion of the stellar disk will be blocked, leading then to either an excess of red or the blue shifted light, which will then lead to a bump in the radial velocities. So what we see here in the bottom left is also a radial velocity curve. It's just zoomed in quite a lot. So the x-axis only goes from minus 0.03 to 0.03 in the phase range of the planet. So, and if we have a look again at the other plot, this is only like a very, very tiny part in the right here in the middle, where this effect basically, where we can see this effect. And yeah, so if the planet comes in from this side, then part of the blue shifted light will be blocked, leading to a positive bump in the radial velocities. Once it reaches the stellar center, then we are basically back to the normal level. And then it goes over the red side, the red shifted side blocks part of that light, and leading to a excess of blue shifted light, which results in this negative bump right here. And then it leaves the stellar disk again. And this Rossiter-McLaughlin, or in short RM anomaly, can look different depending on the orbital configuration of the system. And yeah, here are some examples. For example, an aligned system, which I've basically just shown you. So we have this nice feature with a positive and a negative bump. However, we can also have a misaligned system where the transit, or where the planet might only be transiting across like one of the sides. For example, here over the redshifted side of the stellar disk, and this will then result in only like one bump in the radial velocity curve. And we can also have retrograde orbits where it's just basically the other way around. We start with a negative bump and go to a positive bump, and then back to the standard radial velocity curve. So what we can see from this is that using the RM effect, we can measure the orbital obliquities. So the angles between the stellar spin axis and the planetary orbital axis, which is indicated here with lambda. And the magnitude of this effect depends on quite a few parameters. For example, the planet-to-star radius ratio. So the bigger the planet, the more of the stellar disk will be covered, and the more pronounced will be the bump that we can observe. But it also depends, for example, on the rotational velocity of the star. So if the blue shifted effect or the blue shift effect of the light coming from the star is stronger, or the redshift stronger, then this will also give us a greater effect, but only up to a certain limit. Okay, so let's have a look at these orbital obliquity elements. So we have a star right here with a planet here and its orbit here. Then we have our line of sight indicated by this arrow coming from the bottom left, going to the center of the star. And then we have here the stellar spin axis. So the star is spinning around this axis. And the angle between our line of sight and the stellar spin axis is the stellar inclination, I star. And yeah, we usually cannot measure this super easily, but I will tell you a bit later how we can do that. Then we have the planetary orbital axis. So this is the axis which the planet is orbiting around. And the angle between our line of sight and this orbital axis of the planet is the orbital inclination, which is indicated here with I orb. So the true angle between these two axes is called, or is psi, which is the 3D or the true obliquity. However, since we cannot easily measure the stellar inclination, we can usually only see the sky projection of this angle. So we can only see the sky projection of the stellar spin axis and the sky projection of the planetary orbital axis, which gives us this lambda. This is called the sky projected obliquity. And yeah, to get to the 3D obliquity from the 2D sky projected obliquity, we need this stellar inclination. And yeah, one way to get to the stellar inclination is by monitoring the activity of the star in long duration light curves, for example. So if the star has a star spot, then we might be able to see it periodically by a dip in the brightness in the light curve. But yeah, this is usually not super easy to do. Okay, now let's get into some motivation. So why are we doing this at all? Okay, so there are a few theories regarding the formation and also the subsequent migration of hot and warm Jupiters. So hot Jupiters are Jupiter-sized planets, which are really, really close to the stars, orbiting with just maybe one or even less days, one time around its star. And warm Jupiters, there's some different definitions. Some say it's like that they have to be like 10, have orbital periods of more than 10 days, but usually it's also done with the scaled semi-major axis, which is basically the semi-major axis divided by the stellar radius. And if that value is greater than 10 or 11, then it's also a warm Jupiter. Okay, so for hot Jupiters orbiting cool stars. So cool stars are stars below the so-called Kraftbreak, which basically divides stars with deep and with shallow convective zones. So cool stars have deep convective zones, and this boundary lies at about 6,200 Kelvin. And for hot Jupiters orbiting these cool stars, it seems that they are mainly misplaced by high eccentricity migration with the spin orbit alignments, so the misalignments between the stellar spin axis and the planetary orbital axis being able to be reverted by tidal damping, because tidal damping is more efficient when there are deep convective zones. And hot Jupiters orbiting hot dwarfs, so those with shallow convective zones, they are thought to be not able to be realigned exactly due to this, because then the tidal damping processes will be more inefficient. And for warm Jupiters, it has been found that they orbit preferentially in alignment with their host star's rotation, this completely disregarding the stellar temperature. but there are so far only, well, about 16 measurements of those, and also 2 of those show misalignment, but nevertheless. Okay, now let's have a look at this interesting plot. So radially outwards, we can see the effective temperature of the host star. So for example, 6,000 Kelvin is indicated by this black line here. And then basically around this half circle, we can see the projected obliquity angles, so the lambda angles. And indicated in the different colors, we have hot Jupiters in this sort of lighter color, warm Jupiters in this darker color, and Saturns we can ignore. They're also on here, but we can ignore them for now. And what we can see is that for hot Jupiters orbiting these hotter stars with their Kraftwerk at around 6,200 Kelvin, so about this black line here, we can see that they are scattered basically over all possible angles, more or less. However, there are also a few which are below the temperature and are still misaligned. But we can see that for the most part, the hot Jupiters orbiting these cooler stars, that they are in this area right here, so that they show relatively good alignment with their host star's rotation. And for warm Jupiters, we can see also that they are mainly mostly aligned with their host star's rotation, but the stellar temperature doesn't play an important role here because they are aligned over all stellar temperatures. Exactly. So hot Jupiters around cool stars are mainly aligned. Hot Jupiters around hot stars show various obliquity angles, and warm Jupiters also are generally aligned. So this indicates for us that there must be different migration pathways for these different types of planets. Okay, so there also seems to be a preponderance of hot Jupiters on polar orbits for hot host stars, which is shown by 3D obliquity measurements. Okay, so let's have a look at this. On the left plot, we have the projected obliquities, sort of shown similarly to the plot which we've seen before. We have the stellar inclinations in the middle and the 3D obliquities on the right. Okay, starting with the projected obliquities here, let me zoom in a bit. We have hot Jupiters with cool hosts, indicated by this sort of light bluish color. Then we have hot Jupiters with hot hosts, indicated with the red color, with very hot hosts with orange color. I think the differentiation between hot hosts and very hot hosts is about starts at like 7,000 Kelvin for the very hot host stars. And then we have warm Jupiters and cold Jupiters in this sort of greenish blue color. And the rest we can ignore for now. So what we can see in these projected obliquities, so the sky projection of the 3D angle, we can see that it seems that most of the hot Jupiters orbiting cool stars, indicated by this light blue, are aligned with their host stars. For hot hosts, it's a bit more smeared out, I would say. Various angles are possible, but most of them are still aligned. And then for very hot host stars, we can see that it's distributed relatively evenly over all angles. And for warm Jupiters and cold Jupiters, most of them seem to be aligned. However, there are a few that stray away from this. Then we have the stellar inclinations here, also indicated with the same coloring as before. And we need the stellar inclination to get to the 3D obliquities, as is shown here on the right. And if we now take a look at the hot Jupiters with cool host stars, we can see that, yeah, most of them are still aligned with their measured 3D obliquity. And for the hot hosts, it is interesting because actually most of them seem to be in polar orbit. And the same can be said for the very hot or the hot Jupiters orbiting very hot host stars. And for the warm Jupiters and cold Jupiters, it also seems that most of them are in alignment from the 3D obliquity measurements. However, what I need to mention here is that these are relatively small numbers. So only 23 hot Jupiters orbiting cool hosts, 6 around hot hosts, 8 around very hot hosts, and only 8 warm and cold Jupiters. Okay, going on. We have another slide which is sort of similar to the ones before, but this also shows it quite nicely. So in the top plot, we have the hot Jupiters orbiting cool hosts, hot hosts, and very hot hosts with the same color coding as before. On the y-axis, we have the projected obliquity, and on the x-axis, we have the stellar effective temperature. So if you remember, the Kraftwerk lies at around 6,200 Kelvin, which is right around here. And as we can see, with lower temperatures, it seems that the planets are relatively in relatively good alignment with their host star's rotation. Then once we reach the Kraftwerk, then it gets like more or less smeared out over all obliquity angles. And the same trend is true for the very hot host stars. So on the second plot, we can see the warm Jupiters and cold Jupiters, and also sub-Saturns and multi-transiting systems. But we only need to pay attention to the warm Jupiters and cold Jupiters, which seem to be mostly aligned across like all effective temperatures, except for a few outliers in this range. But still, we don't see the same trend as here for the hot Jupiters. And in the bottom, we can see the rotation rate on the y-axis and the stellar effective temperature on the x-axis. And we can see the general trend that hotter stars basically spin faster and spin a bit slower. And this also has implications for the tidal damping. For example, in the case of orbital decay, so shrinking orbits, slow rotation rates lead to a much more effective tidal damping, which we can see in the orbital decay. Okay, now let's look at what we've really done, or what I've really done. So we have data for 2 warm Jupiters and 4 brown dwarfs from the HARPS North spectrograph. And we have also access, of course, to the already available archival data from, for example, HARPS or other spectrographs. And our first target was 106b, which is a warm Jupiter in orbit around an F-type star, which lies in the temperature very close to the Kraftwerk. And yeah, I've indicated this star sort of in the bottom right, like in terms of its size in comparison to the Sun on the left. And so we have, for the radial velocity observations, we have 2 half nights of HARPS observations and 1 full night of HARPS North observations, in addition to the Sophie and Coralie data sets from the discovery paper. And then for photometry, we have TESS photometry in 4 sectors from 2019 and 2021, where we will actually get the next one in November this year. Okay, now what have we done with this data? So the TESS photometry was analyzed using the transit light curve modeler, or in short, TLCM. And the fit results from these transit fits, they were used as priors for the radial velocity and, well, also the Rossiter-McLaughlin analysis. And the radial velocity data were analyzed using a code based on the analytical calculations for the Rossiter-McLaughlin effect by Harre et al. 2011. And in this code, the Keplerian orbit and the radial velocity, or the Rossiter-McLaughlin effect, are modeled simultaneously. And this model, which we have for the 2 effects, is then optimized using MC in Python. Okay, let's get to the result for the transit in Davis. So these are our phase-folded transits. So on the y-axis, we can see the relative flux. On the x-axis, we can see the orbital phase. And what I mean by phase-fold is basically that all transits that were observed were just stacked on top of each other so that we get a nice clear signal and can measure the parameters nicely. And yeah, we get this nice dip in the light curve, which we expect for this type of planet around this type of star. So this is our radial velocity curve for the system. On the y-axis, we can see the radial velocities. On the x-axis, the orbital phase again for the whole orbit. And yeah, we can see this nice sinusoidal shape. And in the middle, we can see that something is going on, which is the Rossiter-McLaughlin anomaly. Down here, we can see the residuals. Okay, so besides improving the orbital parameters from this fit, we also find a non-zero eccentricity, which is quite small at only 0.05 plus minus 0.01. But we can still see it here actually in this curve because our red model is not crossing the y-axis at the 0 point. And besides finding the small eccentricity, we don't find any further planets, be it in the photometry data or in the radial velocity data. Okay, but since this eccentricity is so small, we need to make sure that not just a spurious case. So we repeated our radial velocity modeling for a circular orbit as well, and compare the Bayesian information criterion, in short, big values, which is a sort of fit statistic, also keeping in mind the number of parameters that are being fitted at the same time. So for the circular orbit, we get a big value of this, so 8,600, and an elliptical, or for the elliptical fit, we get a big value of 8,100. And so the lower value indicates a better fit, making the latter our preferred solution from just this test. But to further validate this eccentricity, we employed the F-test for small eccentricities of Lucy and Sweeney from 1971. This test was developed for binary stars. This is also applicable to our case. And yeah, from this, we find only a small probability of 1.7% for this apparent eccentricity to be spurious, which is below their defined limit of 5%. Oh yeah, from this we conclude that we can adopt the eccentric solution for the system. Okay, so now what we see here is the Rossiter-McLaughlin anomaly in our radial velocity curve, so radial velocity on the y-axis and orbital phase on the x-axis. However, this is zoomed in quite a lot again, ranging only from an orbital phase of minus 0.02 to plus 0.02. So this is really just the middle part of the radial velocity curve, which we have just seen. And just at first sight, I guess it is quite clear if you remember a few slides back that this looks aligned. However, there is some scatter in the data, especially in the second half of the transit, which beats our not super small error bar of 11 degrees. And so what we find is a projected obliquity angle -1 plus -11 degrees. And the size of the error bar is mainly limited by the scatter here, which was caused by clouds during the observations, mainly during the second half of the transit. So we have two data sets which cover this part of the transit. And in both nights, there were clouds. Okay, so from this, we can conclude that the planetary orbit is aligned with the stellar rotation, which is in agreement with the general trend of warm Jupiters and single star systems to be aligned with their host star's rotation, as has been observed by Rossiter 2022. And I also have some remarks on the 3D obliquity, because there has been, just after I put our paper on the archive, there was another paper appearing the next day, basically covering exactly the same topic, just with the different data set. So they had RVs from the NEAT spectrograph, and they find a projected obliquity of 6 plus minus 17 degrees, which is good because it's in agreement with our result. And they didn't use any of the HARPS North or of the HARPS data that were available. So and they also find a rotation period of the star in the test-light curves of 9.77 days, which they can use to infer the true 3D obliquity of the star, which is 26, or which they find to be 26 plus 12 minus 17 degrees. So we also already had a look at the rotation period of the star, but we couldn't really confidently rule out the other results. Maybe they have done something differently from our analysis. But nevertheless, if we still use this result of this rotation period, which we also found one solution for, and then we can convert the 2D sky projected obliquity to the 3D true obliquity using this formula over here, where we need the stellar inclination and the planetary inclination as well. So the planetary inclination is relatively simple because for transiting planets, it's always close to 90 degrees. And this stellar inclination we need to get from example, from like sampling the parameter space using Markov chain Monte Carlo algorithm, for example, to really try to get this as precise as possible, because there's also a degeneracy in the derivation of the stellar inclination. Nevertheless, from this we can get a 3D obliquity angle of 26 plus minus 5 degrees, which is good because in agreement with their value, and the improvement on the error bar is largely driven by our more precise measurement of the V sin I, so the stellar rotational velocity measurement, due to the fact that the HARPS and HARPS-North radial velocities are more precise, and also that we have a lot more radial velocities than they had available in their analysis. Okay, now let's come to the conclusion. So we found that OSP 106b is in alignment with its host star's rotation from the measurement of the projected obliquity in the system. And this adds to the sample of the 16 warm Jupiter systems, which have already measured obliquities, and 14 of which are in alignment with their host star's rotation, which supports the theory of quiescent migration through the disk, like in contrast to hot Jupiters, which are thought to get into their tight orbits via high eccentricity migration, for example, via planet-planet scattering. And as our system, some of these already mentioned 16 other systems show non-zero eccentricities, which can usually be attributed to companion bodies in the system, be it like a second star, a brown dwarf, or another planet in the system. However, this seems not to be the case for our system, but still, given the relatively moderate orbital period of 9.3 days, the eccentricity damping timescale might still be relatively long for this star-planet combination, and also because the star is relatively close to the Kraftwerk, actually a bit hotter than 6,200 Kelvin, meaning that the eccentricity could be primordial. And yeah, I will leave you with this and the archive identifier to the paper, which was just accepted for publication in the Astronomical Journal in the bottom right here. And I'm happy to answer questions from you if you have any. Thanks.